Hello everyone, my name is Mayur B and my USN is 2SD23EC061. Today I'll be demonstrating the way to generate a sawtooth waveform using an external digital to analog converter which is interfaced with an ARM7-based LPC2148 microcontroller board. So the purpose of this demonstration is to show how digital signals generated by the microcontroller can be converted into continuous analog waveforms using an external peripheral. Now let's move into our development window. I'm using Keil µVision software. I've pasted a code program here, but before we take a look at the code, here's a quick heads up. As you can see on the screen, it is not a part of the project. It's just here for explanation. During implementation, while creating the new project, ensure that the board selected is ARM7 microcontroller board, that is LPC2148. And after the creation of the project, make sure to change the settings of the target file so that during the implementation you can get the hex file, so which can be used in the software known as Flash Magic, which allows us to load the hex file onto the microcontroller board. Environment configured, let's break down the C code. At the top of the program, first we include the LPC214x.h header file, which gives us access to the microcontroller's specific registers. We also define a simple software delay function that allows us to help us control the frequency of our wave. Moving on to the main function, we first initialize an integer variable sawtooth underscore value to 0. This acts as our 8-bit digital counter. Next, we set the IO dir 0 to 00FF0000 hex value. This is crucial step that configures the pins P016 through P023 as output pins. These 8 pins serve as the parallel data bus to our external DAC. Inside our continuous while loop, first we set the IO CLR 0 pin to 00FF0000 to clear those specific pins, ensuring no leftover data remains. Then we set the IO set 0 to output our sawtooth value. Because our output pins start at P0.16, we use a bitwise left shift of 16 to align our 8-bit counter perfectly with the hardware pins. After sending the data, we increment the sawtooth value by 1. This steadily increases, which creates a rising slope of the wave. Because we are using an 8-bit DAC, its maximum input is 255. Our if statement checks when the value exceeds 255 and instantly resets it to 0. This reset creates a sharp vertical drop of the sawtooth shape. Finally, a short delay is called before the loop repeats. Once the code is compiled without errors, we use Flash Magic to implement our generated hex file onto our LPC2148 board using the serial ISP connection. Moving to the hardware setup, you can see that the LPC2148 development board here, the GPIO port pins of port 016 to port 023 are wired directly to the digital inputs of our external DAC IC. We also have the reference voltage and ground connected appropriately. Finally, to observe our generated waveform, we connect the analog output pin of the external DAC to the positive terminal of our CRO probe, ensuring the black alligator clip is securely connected to the common ground of the board. Now let's look at the output. As you can see on the oscilloscope, we are successfully generating a continuous sawtooth waveform. This linear voltage ramp corresponds to our incrementing counter in the code, and the sharp vertical drop occurs exactly when the counter resets to 0. By adjusting the delay loop in our code, we can easily modify the frequency of this waveform. This concludes the demonstration of generating a sawtooth waveform using an external DAC and the LPC2148. Thank you.